Okay guys, in this next video we are going to talk about acid and base type reactions. Acids and bases are a very important class of electrolytes in both chemistry and also biology. Um, Acids and bases can be molecular compounds or they can be ionic compounds. And they have some characteristic properties. So acids are known for their sour taste. For example, citric acid is the active ingredient in many sour fruits. Um, Acids undergo certain types of chemical reactions. So, for example, if you take litmus paper, if you take blue litmus paper and dip it in an acid, it will turn that litmus paper red. Bases, on the other hand, are regarded as having a sour taste. They have a sort of a soapy texture to them. And then they have, in a sense, the opposite effect of acids. So if you have red litmus paper and you dip it in a base, it turns it back to blue. So acids and bases are kind of like two sides of the same coin, so to speak. So you find, in everyday experience, you'll find acids used a lot in different foods, right? So we've got our fruits, and then we've also got, vinegar. The active ingredient in vinegar is acetic acid. You'll also find acids used in some types of cleaning products. Bases find all sorts of uses in agriculture as well as cleaning products, in addition to that. And so they're kind of everywhere in society. So acids and bases are an important class of compounds. Um, Acids and bases are electrolytes, and they can also be classified as being strong or weak, just like electrolytes can. Strong acids and strong bases completely dissociate in aqueous solution. And I have a list here of strong acids and strong bases that you need to commit to memory. So we have perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. So these are our strong acids. If you encounter an acid that is not on this list, you are to regard it as a weak acid. We have the same situation for the bases. Lithium, sodium, and potassium hydroxide are all strong bases. Note that these are all group 1 cations. Also, calcium, strontium, and barium hydroxide are also strong bases. And so these are group 2 cations, the heavier group 2 cations. If you encounter a hydroxide or some other type of organic base that's not on this list, you're to regard that as a weak base. And in contrast to strong acids and bases, weak acids and bases, they do not completely dissociate in aqueous solution. And I'll show you some examples of that as we go. I'm going to review two basic ways of thinking about acids and bases. The Arrhenius concept of an acid is a substance that produces protons in solution. Instead of thinking of protons, you can also think about forming hydronium, and that's because of the following type of scenario. Protons, so just a proton with no electrons, is not very stable in aqueous solution. It will always find a water molecule to form hydronium. And so in this sense, H plus and hydronium are essentially the same thing in solution. You'll never find a bare proton by itself in solution, or at least not for very long. Rather, you'll always find the hydronium form. So you can actually use the proton and hydronium interchangeably. They essentially mean the same thing. So according to Arrhenius, an acid is a substance that produces hydronium ions in solution. A base is a substance that produces hydroxide ions in solution. And so what I've shown you here are two dissociation reactions. We have nitric acid here. The ion or the proton leaves the NO3 group, which gives us the proton and the nitrate, and then this proton is going to go find a water molecule and form hydronium. For sodium hydroxide, this is more of a dissolution reaction. Sodium hydroxide is an ionic compound. It's a solid. It's a white sort of crystalline substance. If you drop that into water, eventually it will dissolve, and you'll have separated sodium ions and hydroxide ions. Because the hydroxide ions are formed, Arrhenius classifies this as a base. Okay, so acids produce hydronium, bases produce hydroxide in solution. A different way of thinking about the acids and bases is given to us by this Bronsted-Lowry concept. And it involves the idea of a proton transfer reaction. And that's something that you want to associate with acid-base chemistry, the transfer of a proton from one species to another. According to Bronsted and Lowry, the acid is a species that donates the proton, and the base is the species that accepts the proton. And so I've got two examples here. Going back to the nitric acid, this time I've included an explicit water. And the idea here is that when the nitric acid reacts with the water, it donates a proton to the water, which forms the hydronium. And that leaves behind the nitrate. So the nitric acid is the acid because it donates the proton. And in this reaction, the water, because it accepts a proton, is acting as a base. Okay, so in this proton transfer reaction, you have an acid and you have a base. The acid donates the proton. The base accepts the proton. I have another example here. This is ammonia. Ammonia is the quintessential example of a weak base. In this case, ammonia accepts a proton from water. So a proton is donated from the water to the ammonia. That gives you the ammonium cation, and it leaves behind hydroxide. So in this reaction, the ammonia is the base. It accepts the proton. The water, in this case, is the acid. It donates the proton. Notice that in this first reaction, water acted as the base, but in the second reaction, water acted as an acid. A species that can act as either an acid or a base is called amphiprotic. You'll also notice that I used a one-directional arrow for this acid dissociation reaction of nitric acid, but I used a bidirectional arrow for the base dissociation reaction. And that's because nitric acid is a strong acid. It essentially 100% goes to this dissociated form. However, ammonia is a weak base. It only partially dissociates into its ions. And so whenever you have a weak electrolyte, a weak base in this case, you use the bidirectional arrow. Really, only a small fraction of the ammonia dissociates to form these ions. Most of it is in its molecular form. Well, here's my slide on hydronium. It's a water molecule with an extra proton. I basically covered all of this stuff here. So I'm just gonna move on since I've already said all of these things. So here what we're gonna do is we're gonna practice writing out our acid and base dissociation reactions for different species. For HCl, I'm gonna do this two ways. First, I'll do it without an explicit water molecule. It's a strong acid, and so 100% of the HCl that's dissolved in water is going to dissociate to form ions. So this is one way that you can write the acid dissociation reaction for HCl. Another way is to explicitly include the water. And here what we're doing is we're setting up the proton transfer. So we'll have a proton transfer from the HCl to the water. That's going to give us hydronium, and it's going to leave behind chloride. Okay, so two ways that you can represent the acid dissociation reaction. They're equivalent to one another. Okay, so there's really no distinction. We've already seen the reactions for nitric acid, so I'm going to skip that one. And I'm going to go into this weak acid, this hydrocyanic acid. Here, let's see, this should be N. I'm going to go ahead and just focus exclusively on the proton transfer reaction here. I prefer that. Here, the acid transfers a proton to the base, the water in this case. That gives us our hydronium, and it's going to leave behind a cyanide ion. Notice I've used the bidirectional arrow because this is a weak acid. It's not on our list of strong acids. Likewise, hydrofluoric acid is not on our list, so it is also a weak acid. And it does the same thing. It donates a proton. That gives us hydronium, and it's going to leave behind a fluoride ion. We've already done the bases, but I'll indicate them as well. So sodium hydroxide here, it's a solid, and it's a strong base. I'm going to put the water up above because this is just indicating that the sodium hydroxide dissociates. It's going to give us sodium plus and hydroxide. Okay, and it's the production of this hydroxide that makes this a base, and in fact, it's a strong one. We've already seen the ammonia reaction, but it's important enough that I will write it again. Ammonia reacts with water. The base accepts a proton from the water. It's a weak base, so I use a bidirectional arrow. This is going to produce the ammonium cation, and it's going to leave behind hydroxide. And so you want to get into some practice of writing out acid and base dissociation reactions. So I encourage you to use the end of chapter questions of the textbook to practice these. Here we'll get a little bit more practice in. Let's flip the page here. Okay, so we're being asked to complete these reactions. And so for part A, we have perchloric acid, which is a strong acid, reacts with water. The acid donates the proton, so that's going to give us some hydronium, and it's going to leave behind a perchlorate ion, like that. Hydrobromic is very similar to the examples that we've seen already. Hydrobromic acid donates its proton. It's a strong acid, so I use a one-directional arrow. It's going to leave behind a bromide, in addition to producing some hydronium. Next, we have some conceptual questions. Which of the following statements is true? HBr is partially ionized in water. That's not true because hydrobromic acid is a strong acid, so it completely dissociates, completely ionizes in water. Perchlorate completely ionizes in water. Yes, that's true. Perchloric acid is a strong acid. In the solution of hydrochloric acid, you expect to find very few hydrochloric acid molecules relative to perchlorate ions. That is true. Because perchloric acid is strong, most of the perchloric acid is going to be in this ionized form. In HBr solution, there are significant quantities of hydrobromic acid in its molecular form. That is false. Hydrobromic acid is a strong acid. It completely dissociates, so there's going to be very little molecular HBr dissolved in solution. If it were a weak base, for example, if we go back to the ammonia example, most of the ammonia would be in its unionized form because it's a weak base. Okay, so that's the difference between strong and weak acids and bases. So in this example, we're really just testing our recall of the list of strong acids and strong bases. Lithium hydroxide is a strong base. Acetic acid is a weak acid. Hydrobromic acid is strong. nitrous acid. Notice the 2, it's not a 3, so this isn't nitric acid, this is nitrous acid. This is a weak acid. Phosphoric acid. It looks like it might be strong. Look at those 3 protons that it has. It's actually weak. This is not on our list of strong acids, so this is a weak acid. Hypochlorous acid here, also weak. Perchloric acid, this is on our list of strong acids. It's a very strong acid. Strontium hydroxide is a strong base. It's on our list, and so we need to know that one is a strong base. Okay. In this next slide, we're talking about the reaction between acids and bases. Acids and bases, when they react together, are said to neutralize one another. And this usually produces water, not always, but often produces water. And it results in an aqueous ionic compound, which we call a salt. So the products of an acid-base neutralization reaction are an ionic compound that we call a salt, and then possibly water. And I've given you 3 examples here. We have a strong acid, hydrochloric acid, and a strong base, calcium hydroxide. They react together to neutralize one another. You get water is being produced, and then the calcium chloride is called the salt of hydrochloric acid and calcium hydroxide. Here we have a weak acid, hydrocyanic acid, reacting with potassium hydroxide. It produces water, and the salt that's produced, potassium cyanide, is the salt of this acid and this base. In this last reaction, we've got sulfuric acid reacting with ammonia to produce ammonium sulfate. No water is produced in this reaction. However, we do still call ammonium sulfate the salt of sulfuric acid and ammonia. Okay, so these are typical examples of neutralization reactions. And here we are going to write out different neutralization reactions. So we're going to get some practice writing these down. So from words, hydrobromic acid. So this goes back to our nomenclature skills. Hydrobromic acid plus sodium hydroxide. What happens is the hydrogen is going to pair up with the hydroxide. The salt that we're going to get left behind is going to be the sodium bromide, aqueous, and water is being produced. Here they're asking us to write out the net ionic equation. Okay, take your strong electrolytes, the hydrobromic acid, break them up into their ions. Sodium hydroxide is also strong. Sodium bromide is a strong electrolyte, so we can break that one up as well. Water, however, is not an electrolyte. We leave it alone. Cancel out your spectator ions, the bromide and the sodium. That gives us H plus OH minus produces liquid water. And so the net ionic reaction here for this strong acid, strong base is just the production of water. In fact, that is true of every strong acid, strong base. Let me show you another one that's just like that. So we'll look at the hydroiodic acid with calcium hydroxide. So we're going to need 2 equivalents of hydroiodic acid. That's going to form the aqueous calcium iodide salt. And we're going to get 2 equivalents of water out of this reaction. So here I've balanced the molecular equation. Write out the total ionic equation. 2H plus 2 iodides, calcium 2 plus 2 hydroxides, calcium 2 plus 2 iodides, and then we leave the waters alone. Cancel the spectator ions, the calcium and the iodide. And then we're going to have H plus OH minus gives us water. We can reduce the coefficients. You're going to wind up with H plus hydroxide giving you water again. Okay? So the essential chemistry of any strong acid, strong base always involves the production of water. It's always true. I will let you work out part C on your own because part C is another strong acid, strong base. Let's look at part D, which involves a weak acid, nitrous acid. See how it's different. So nitrous acid has this chemical formula. We're reacting with sodium hydroxide. Okay, we are going to end up producing sodium nitrite, aqueous solution, that's the salt, and then the water, right? The proton combines with the hydroxide to make a water. The total ionic equation is a little bit different here because nitrous acid is a weak acid, so we don't break it up into ions. We leave it in its molecular form. Sodium hydroxide, however, is strong, so we'll break that one up. The sodium nitrite is a strong electrolyte, so it gets broken up. And we leave the water alone. Cancel our spectators. And what are we left with? This is the net ionic equation. For this weak acid, reacting with the strong base. Part E is going to be very similar to this one. Lithium hydroxide is a strong base, and then the thiosulfuric acid is going to be a weak acid. Okay, so I'll leave that one as an exercise for you. You'll have to figure out what thiosulfuric acid is. Well, I think that is the last slide in this one. We will start the next video with oxidation reduction reactions.